Okay, now ready for some more math? Do you remember when we were doing equate chapter 2? We went here and we did this really scary looking all of this math. Oh yeah, here. Do you remember doing all of this stuff for a line charge at a point? And we steps to follow 1, 2, 3. We figured out what the forces were, and we calculated it, what the E fields were, and all of that long math. Do you remember doing that? And in the end, we were like, oh yeah, there's an easy way to do it, and it's called the Gauss's law. I want to show you the really scary way of doing it, and then I want to show you the Ampere's law, which is literally equivalent to what we've done before. So it's not new. It's the same thing, except now instead of talking about electric fields, we're talking about magnetic fields. Are we ready to do the scary math? Come on, it's character building. Okay, just like we did for electric fields, I want to do a long straight wire. Everybody ready? So we are going to, when we did it in chapter 4, we did a long straight wire where the charges were embedded into the wire, correct? And then we found the points inside and outside. Here, the charges themselves are moving. And now instead of the electric field, the moving charges will create what kind of a field? Magnetic field, right? So look at the similarities between the two, and then you should be able to say, oh, should the steps be pretty much the same? Yeah. Should the math be pretty much the same? Yeah. Everything is going to be pretty much the same, except instead of using E's, we're going to call them B's. Ready? Here we go. We should be able to do this in the next 10 minutes. Okay. Ready or not, here it goes. So I have a wire. And I want to find the B field at this point, P. Just like we did there, let's choose a small segment, DZ, again, normal coordinate systems, X pointing out of the paper, Y and Z going upwards. So let's choose this as DZ. My DL is the segment that's moving upwards. Let's find it. Let's find the B field at point P. Here's another. This is going to be my funny looking R now. This is my angle theta. Let me call this angle pi minus theta. Let's call this distance Z. Call this distance D. Theta, remember, is the angle between DL and R. And we are doing this for a long, straight wire. Just like we started on when we were doing the electrostatics, we are going to do a long straight wire. Okay, looking at this picture, where is the eye going? The direction of I is here. May I write sine of theta equals sine of pi minus theta equal d over funny looking r. And then may I write sine of theta as d over z squared plus d squared square root. Okay, stare at it. Okay, so following our regular steps, the ones we did before, the first step was divide the wire into small elements of length dz. Step 2, in the segment dz, may I write the segment dz as I times dl. This is where dl is the distance dq moves in time dt. May I write this as v equal dl over dt? May I multiply both sides with dq? Will this become dl over dt over dq dq, or dqv equals I dl? Okay, this is my orange equation. Did I write any other equation with orange? What do you guys want to call this equation? I'm just going to call this the tulip equation. Everybody write that equation down. I'm going to try to make sure I don't mess it up. Okay, I'm going to write my tulip equation here. What was it? dB equal mu naught over 4 pi I dl sine theta over the funny looking r squared. Okay, in this case, is the direction of dl and dz the same? So may I rewrite this as, since dl is the same as dz, may I rewrite this equation as mu naught over 4 pi I integration dz sine theta over r squared, or mu naught I over 4 pi integration. What is sine theta? D over square root of z squared plus d squared 1 over z squared plus d squared dz. I just plugged in the values. And my limits of integrations will be minus L over 2 to L over 2. Or I can rewrite this as mu naught I over 4 pi integration d over z squared plus d squared 3 over 2 dz from minus L by 2 to L by 2. So that means integrate. Do you guys want me to show you the steps in the middle? Are we good? No? Okay. There's like there's like about four or five steps in the middle. No? Nick says no. Okay. Well, the answer then comes out to be mu 0I over 4 pi d L over square root of L over 2 squared plus d squared. Drum roll. And I will put it in a box. And as always, we also have to do the limit for a very long wire where L will be much, much greater than D. Remember, L is the length of the wire and D is the distance. This will reduce down to B equal mu naught I over 4 pi D L over L squared over 2 square root. Square roots get canceled. And we will be left with B equals mu naught I divided by 2 pi D. Now, this took like 1,000 steps, right? Do you want to do all of this in 3 steps? Okay, 4. Excellent. That is called Ampere's law. Just like Gauss's law, there was a guy called Ampere who came up with his own law. And what it says is, do you guys remember what Gauss's law was? Integration E dot dA equals Q enclosed over epsilon naught. Can you guess what this law would sort of look like? Replace the E with a B, replace the charge enclosed with the current, replace the epsilon naught with the mu naught, right? And so the Ampere's law looks like this. And it's not over the area, it's over the loop. So basically what the Ampere's law is you take a long straight wire and you draw a circle around it that encompasses the D you want, right? That was your point that you were looking at it. What is wrong with you? At a distance D. And in that, what you will do is you will say, well, B is constant, integration still over DL equal mu naught I. Integration over DL will result in R d phi mu naught I. What is R in my case? D. B dot D. What is integration over 2 pi from 0 to pi? 2 pi. Drum roll. B equals mu naught I divided by 2 pi D. Does that equation look familiar? Three steps or less versus whatever this mess was. And we didn't even fill in this. We should write here and some magic happens. Or that. Which one would you prefer? Right? The Ampere's law. So from here on out, tomorrow, starting tomorrow, we will focus on Ampere's law.